Hello, this is Dr. Lukes, and this is the second in our series of lessons to replace class on August 31st. We're going to be looking at diffusivities of electrolytes in liquids in this case, and then we're going to look at biological solutes in water and in biogels. So the equation that is recommended for electrolytes is given here. We'll look at it briefly. It's roughly 9 times 10 to the minus 10th times the temperature times these 1 over n's, that's the valence. So 1 over the valence for the positive ion, 1 over the valence of the negative ion. And then we're going to divide by the sum of the reciprocals of the ionic conductances for very dilute solutions. And the values of these conductances, because you probably don't know these, are given in table 633 of our textbook. Now, a lot of times this is expressed in a different way in terms of diffusion coefficients, not really a diffusivity, but a diffusion coefficient for a single ion. And if we're going to do that, we can relate this conductance to the valence using this expression here. And that then allows me to rewrite this formula for diffusivity in terms of these constants here. Okay. Now, when you need this, you're going to need to look it up. I'm not going to expect you to remember this, but it's just a matter of chasing all of the pieces and finding the data, putting it together, and you too can come up with an estimate for diffusivity. But you needed to know in this case that you were looking at an electrolyte solution. What if you were looking at biological solutes? Well, again, you need to find the equations that are appropriate for that. And in this case, there are two that are recommended. In general, we use the Stokes-Einstein equation, which is 9.96 times 10 to the minus 16th times the temperature divided by the viscosity of, generally it's water, these are usually aqueous solutions, divided by the velocity of the solute to the 1/3 power. And if we have a very dilute solution, then we're going to instead use this variation here, where instead of taking this molar volume equivalent, we're going to take the molecular weight of the solute that's trying to diffuse through my liquid water. Diffusion coefficients that you're going to see for these are given in this table here. Notice that in meters squared per second, they range from 10 to the minus 9th to 10 to the minus 11th. And that's simply that biological solutes tend to not move as easily as some other liquids. Okay, they're larger molecules, noted by the large molecular weight, and so they are going to be a little bit more difficult to move randomly through the liquid. Another special case for biologicals is the biological gel. Normally these are gelatin or agar that we're using as our gel, and we have different solutes that we might put in there. Typical are like the sugar family. Okay, and some values of these are given in table 642. And you'll see that there's not a huge amount of variability. Okay, they all are fairly similar to each other. Okay, but they're going to vary with weight percent of the gel solution. Okay, so this is a limited table. If you do need this information, you'll probably want to look that up. Now I'm going to add one last little topic that I need to cover it in this chapter, and it's in a section that we're not going to cover until the end of chapter 7. So I want to talk briefly about distribution coefficients. You actually already know this. A distribution coefficient for our purposes is going to be a concentration at a location, so N sub m is indicating a location, in the liquid compared to what it is on the surface at that same location. Okay? This really is what vapor-liquid equilibrium is describing to us. It's the X over the Y composition. Often we're going to be able to assume that this capital K is 1. Now this doesn't really pertain too much if you're just looking at diffusion within a single fluid, but in the next chapter we're going to come back in and look at what happens as we have things moving from one fluid to another fluid, or maybe into a solid. And so those surface action is going to be very important. Okay. Now we do have one last topic for this chapter, and that's going to be to look at what happens in solids. So we've covered gases, we've covered liquids. Let's next look at solids. Thank you very much.